Calculating equilibrium composition from an equilibrium constant. Okay, so the first issue we have right here is we've been given the initial number of moles of two species in our balanced equation, but we haven't been given the concentration. So, we're going to have to calculate the concentrations first. So we've got the number of moles of oxygen. So we can calculate the concentration of oxygen. Remember, those square brackets is just shorthand for the concentration of whatever is in the square brackets. So there's 2 moles of oxygen and the volume is 500 milliliters. So you need to convert milliliters into liters as well. And we can do that because we can use our equivalency that 1 milliliter is exactly equal to 10 to the power of minus 3 liters. All right, so stick that in your calculator, see what you got. Milliliters will cancel out, giving us units of liters. And I calculated 4 moles per liter, or molarity. So 4.0 molarity for oxygen. And we were also given the initial concentration of the nitrogen monoxide. So we'll do it like we did it in Gen Chem 1. So 0.7 moles of nitrogen monoxide in the same volume, obviously, same container, same volume. So 500 milliliters of that, and 1 milliliter is still 10 to the power of minus 3 liters. So that volume in milliliters will cancel out, giving us units of moles per liter, which is totes appropriate for concentration units of molarity. All right, so that should shake out to be 1.4 molarity. So now we have our initial concentrations of one of our reactants, O2, and our product, nitrogen monoxide. So we can infer from the question that we start out with an initial concentration of nitrogen of 0, because if we weren't told there was any in the flask, then it can't have a concentration. So very sort of quick and dirty looking at those numbers, I'm going to say that this reaction is actually going to proceed to the left, okay? So from products to reactants in order to reach equilibrium. But if you couldn't tell, for instance, if you had a little bit of everything, you would have to write the equilibrium constant expression, which we're going to have to do anyway, and then you would substitute in those initial concentrations to work out your reaction quotient and compare that to your equilibrium constant to determine which direction your reaction is going to go to reach equilibrium. So we've got a stoichiometric coefficient of 2 for the nitrogen monoxide in the balanced equation, and nitrogen and oxygen each have a stoichiometric coefficient of 1, so they don't get a power, but the nitrogen monoxide does. And we have been given the value of the equilibrium constant, which is 4.37. We're going to need that later. So if I calculate my reaction quotient Q by substituting in those initial concentrations, my initial concentration of nitrogen monoxide was 1.4, and that's going to be 1.4 squared on the top. And then on the bottom, initial concentration of nitrogen is 0. And then initial concentration of oxygen, we just calculated as being 4.0. And of course, if you try and stick that into your calculator, it's going to yell at you because you're dividing by 0. So dividing by 0 makes something infinity, right? So basically, Q is going to be much bigger than K. And that is telling us that the reaction is going to proceed to the left, from right to left, in order to reach equilibrium. The sort of quick way of looking at this is, we know for our equilibrium constant expression, it's products divided by reactants. And if we have a 0 on the bottom, that means the concentration of our reactants is too small, right? We've got way more products compared to reactants than we need. So in order to redress that balance, our reaction has to proceed to the left, from products to reactants. So reaction goes to the left. Well, this is a good example to pick because most of the time our reactions go to the right, don't they? So we're going to be going to the left. So now I'm going to write an ICE table, or a rice table if you prefer. So some textbooks have rice with reaction at the top. So you are going to list all your reactants and products in terms of their concentration. So we've got nitrogen, oxygen, and nitrogen monoxide. And then we can fill in the initial concentrations because we know them, and that's what the I stands for. I is for initial. So those initial concentrations in terms of molarity, we start out with 0. for our nitrogen. We start out with 4 for our oxygen. Sometimes you'll be given concentrations, but this question's making us work extra hard. And then we start with 1.4 molarity of nitrogen monoxide. So the change row is where all the thinking comes into it, okay? So for the change row, we are going to write in terms of algebra how our concentrations of our reactants and products are going to change as we proceed towards equilibrium. So you're going to make it easy for yourself. You're going to look at the balanced equation and you're going to pick one of the reactants or products that has a stoichiometric coefficient of 1, and the change in the concentration of that particular reactant or product, you're going to make that your X, and then you can just compare everything else to X. Now, because I know my reaction is going from right to left, from products to reactants, both of my reactants, they both have a stoichiometric coefficient of 1, so it could be either of them that I pick for my X. And that change I'm going to write as plus X because we are forming more of our reactants because the reaction is going backwards. So we're going to increase the concentration of dinitrogen by plus X, whatever X may be. We can relate that to the change in concentration of oxygen. Now, the molar stoichiometric ratio between them is 1 to 1, right? Just 1 in the balanced chemical equation. So oxygen concentration is also going to increase by plus X. So if we look at the product side, the reaction is written, 1 mole of nitrogen combines with 1 mole of oxygen to make 2 moles of nitrogen monoxide. So we have to take stoichiometry into account. So if we're going backwards, 2 moles of nitrogen monoxide are decomposing to form nitrogen and oxygen gas. So the change is going to be minus because the reaction is going backwards, and it's going to be minus 2x because it's going to take 2 moles of nitrogen monoxide for every 1 mole of nitrogen and every 1 mole of oxygen. So that's the hard part. We've done our change row. So then to get our equilibrium row, we are just going to be writing the equilibrium concentrations in terms of X. So the way to get to them is that you're going to add together down each column your initial and change to get to your equilibrium concentrations. So 0 plus X is just going to be X. 4 plus X is just going to be 4 plus X, just adding down each column. And then 1.4 minus 2x, we'll just write that as 1.4 minus 2x. So the key to solving these kind of problems is you can now substitute these equilibrium concentrations in terms of your unknown x into the equilibrium constant expression that we already wrote, and we know the value of k, the equilibrium constant. So then it's just a case of algebraically rearranging and solving for x. Okay, so I guess we're going to have to do that then, aren't we? So just as a little reminder, we do initial plus change, and that will give us our equilibrium down each row. All right, so I'm going to do it. I'm going to substitute in my equilibrium constant expression. So K equals the concentration of nitrogen monoxide squared. So these are the values I'm talking about substituting into the equilibrium constant expression. So let's take that equilibrium concentration of nitrogen monoxide in terms of X, that's 1.4 minus 2x. And do not forget your stoichiometry. So of course that is going to be to the power of 2 because of the squared in my equilibrium constant expression. And then on the bottom is going to be the concentration of nitrogen, which is going to be X, times the concentration of oxygen, which is going to be 4 plus X. So hopefully you guys remember how to do algebra. I know it's been a while. All that is going to be equal to what our equilibrium constant actually is, which is 4.37 given to us in the question. Okay, so we're going to multiply out all these brackets and it's going to be a mess, and then we're going to tidy it up, okay? So 1.4 minus 2x squared. I'm going to just take that 2 brackets and multiply that out. And then on the bottom, we're going to have 4x plus x squared on the bottom, right? What's an easy way of doing this? Here we go. It's not quite the prettiest thing. And then all of that, all your is going to be equal to 4.37. Don't forget about that. Okay. So multiplying out those brackets then on the top of that fraction, 1.4 times 1.4, going to give me, yeah, 1.96. I was right. Okay. 1.96 minus 1.4 times minus 2x, right, is going to be minus 2.8x. And then minus 2x times my 1.4 will be another minus 2.8x. And then minus 2x times minus 2x is going to be minus 4x squared. Let's see if I can make this a little bit prettier. Okay. And then that dividing by what we already got on the bottom equals 4.37. So we can take our 4.0x plus x squared and times it by the 4.37 to get rid of that stuff on the bottom. So that's going to be 4.0x plus x squared. Let's make that look pretty so you can all see what we are doing here. So I'm going to have to multiply all that out as well. Oh, patience is a virtue. All right, so let's multiply all that out as well. So I'm just going to cheat a little bit and do a copy and paste here. So of course that is still square. So 4.37 times 4 is going to give me 17.36. Sorry, I had to check that one. 17.36 plus 4.37x squared. Okay, now I have everything out of those stinking brackets. And now I should be able to rearrange and gather my like terms. You remember doing that in mathematics a long time ago in a galaxy far, far away. I've forgotten something. I've got an x there. Naughty me. 4.37 times 4x. That is 17.36. I know I've checked myself twice on this now, haven't I? 17.48. I know it didn't look right. Silly me. Right, okay. So now we're going to gather our x squareds and our x's and our stuff without an x. So sad, no x. So minus 4x squared, bring the 4.37 to this side. So minus 4 minus 4.37 is going to give me 0.37x squared. All right, and then what about the x's? Minus 2.8 minus 2.8 is, and then minus 17.48, gather those all together will be minus 23.08x. And then what about my just the numbers? I've got 1.96, and then I've got nothing else on that side, so just plus 1.96. Oh. That seems a little anticlimactic. All right, so I've got a quadratic, okay? I've got a quadratic, and A equals minus 0.37, B is minus 23.08, and C is plus 1.96. So you can stick those into your quadratic formula and get two possible solutions for x. You can either use the, quadratic formula, or nowadays a lot of calculators will just do that for you. The point is you are going to get two solutions for x, right? For a quadratic, that's how it works. So sticking that into the quadratic formula, I get x equals minus 62.5 blah 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 blah, or x equals 0.0848. Take a second and realize what you just did, right? You solve for x, which look in your change row of your rice table, okay? You've got the x representing the increase in concentration of nitrogen or oxygen. In this case, it's the same, okay? So don't just be like, I've got a number, I've finished. We've got to substitute this number in to calculate the thing we're asked for, and we have to decide which of these values of x is valid. So I'm going to look at my equilibrium concentrations, and I see the equilibrium concentration of nitrogen is just x. So straight away I can see that I am going to discount the negative solution for x, because it's not possible to have a negative concentration. That makes no sense. And in fact, you can see if I substituted minus 60 whatever it is into any of these equilibrium concentrations in terms of x, I would get a negative number, which makes 0 sense. Okay, so I'm going to select the correct value of x as being the 0.0848. value. So what I was actually asked for was calculating the equilibrium molarity of O2. So this is where you've got to be careful, right? We're going to substitute into our expression for the equilibrium concentration of oxygen, which was 4 plus X. So just getting X isn't enough, okay? Unless your equilibrium concentration of the thing you're interested in happens to be X, right? You're usually going to have to substitute X into one or all of those equilibrium concentrations in case, depends what you ask. So 4 plus X will be 4 plus 0.0848. So that is going to give me, bam, 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 a concentration in terms of molarity of 4.0848 molarity. Now, what will we ask for in terms of sig figs? Round your answer to 2 decimal places. So that means I'm going to ixnay on that last 2 decimal places, get rid of the 0.48, and my answer will just be 4.08 molarity. So obviously, when you're working out these kind of questions, every ICE table is going to look a little bit different because you can have different initial concentrations. Your change row is going to be different because your change row is going to go off your reaction stoichiometry, okay? Your equilibrium row is going to be different because it's going to depend on what your initial concentrations are and what your changes are in terms of X. So the key thing is, sometimes you're going to need to work out the reaction quotient to determine the direction in which your reaction is going to proceed. So you know if you're working in minus X's or plus X's. And remember, when you solve for X, if you have to solve a quadratic, you've got to pick the right solution for X, because solving a quadratic always gives you 2 solutions. And last but certainly not least, getting X is usually not the answer that you're being asked for the final solve of the problem. You're usually going to be asked for 1 or more equilibrium concentrations. So you've got to substitute that X back into one of those equilibrium concentrations in terms of X that you just came up with. All right, so lots of different possibilities. The more you practice, the easier it will get. Have fun.